I will now enter problem 8, but before I enter problem 8, I want to evaluate with you what actually a solenoid is doing. And I hope I will convince you with 2 problems that I will do in a row, that you should never abandon Faraday's law, never amend it. It's unwise, it's unnecessary, it is risky, and it only leads to wrong and incorrect answers. It may work once in a blue moon because you happen to know the answer, but it is conceptually completely the wrong way to think. Whenever you have a non-conservative field, Kirchhoff's law does not hold. The one that says that the integral of E dot dl, closed loop integral, is 0, does not hold. Let's first evaluate how a solenoid works, because we're going to need that. Suppose we have some resistor here, and we had some battery here, and this solenoid had a length L. So this is a solenoid. It has N windings, and let us assume that these are circular, close to circular windings, which have surface area pi r squared. The first question that I want to answer is, what is the magnetic field inside the solenoid? There will be a current flowing which will change with time, because this solenoid has the ability to influence the increase in current. In this case, when I throw a switch, the current will increase. The solenoid will try to hold that down. We call that Lenz's law. But at any moment in time that I have a current IT flowing in this circuit through the solenoid, let's assume that my B field is pointing upwards. Depends on the helicity of the coil. And let's assume that the B field is only finite and constant inside the solenoid, 0 outside here, 0 outside there, and even 0 outside there, which is a little bit of an approximation. So we only assume that the B field is inside. I now forget for the time being Faraday's law. I am going to calculate the B field inside, and for that I choose Ampere's law. This side y, this also y, and the length here is very large. If there is any magnetic field here, it would be perpendicular to the side. Certainly inside the solenoid it's perpendicular to the side, and so the dot product B dot dl would vanish. So I have the closed loop integral of B dot dl equals mu 0 times I through. There is no displacement current if I choose this as my flat surface. There's no changing electric field going through this surface. The B field is only defined inside the solenoid. B dot dl right here is 0. There is no B field outside. At least if I choose this far enough away, the B field here will be 0. And if there is any B field here, it will be perpendicular, so I can ignore that. So what do I get when I make this closed loop integral going around clockwise in the direction of B? I find that B times y equal mu 0 times I. But now this is a soap film, flat soap film, and the current penetrates several times through this soap film. How many times does it penetrate through this soap film? Y divided by L times N. This is the number of times that it pokes through. I have to take that into account in Ampere's law. I lose my y, and I find a result that you have seen before, that the magnetic field in a solenoid equals mu 0 times I times N divided by L. And notice it's independent of the cross-sectional area of the solenoid, little r, and it is also independent of y. It better be independent of y, because Maxwell couldn't care less about how long you choose this. So far so good. We now have the magnetic field inside the solenoid. Now I want to calculate, in anticipation of Faraday's law, a closed loop integral E dot dl I know I'm going to need, sooner or later, when I deal with solenoids, this term, ddt times b dot dA. I will ram it down your throat once more. This is a closed loop. And this is an open surface attached to that loop. Now, if you look at this circuit, then the closed loop that I will choose is the loop that goes through the wires. I crawl inside the wire of the self-inductance. I come out here, I go through here, and I enter up here. That is my closed loop. That is my closed loop integral E dot dl, and I always go around in the direction of the current. That's my convention that avoids that I get unnecessarily minus signs where I don't want them. But now you have to choose a surface which is attached to this closed loop, and that is very hard to imagine. And the way I normally do this when I lecture 802, I dip this whole circuit in soap. And when I dip this in soap, you get a soap film here, but you get a very peculiar staircase soap film in the solenoid. The solenoid, the surface of the soap film is like the surface of the staircase of a spiral staircase that goes up. I have a soap film here, a soap film there, and the soap film rotates around, keep going up and up and up and up and up, not unlike this situation here. Not unlike that. The boundary of the solenoid is this line, and the surface, which is this soap film, is the staircase itself. Maybe we can look at it from above, and you can see it again a little better. It is a very hard to understand surface, but what counts is, and what is important, that the magnetic field pokes n times through this staircase surface, and therefore when I calculate this term, the magnetic field, which I will ignore here, I will assume that even though there is a current flowing here, that the magnetic flux going through this film is almost negligible, but here it's very strong, the magnetic field. I now have to take into account that this magnetic field goes n times through this open surface. And so what now is this term? Well, the integral of b dot dA over that open surface, that staircase surface, first of all it is b itself. So that is mu 0 times I times n divided by L as a start. But now I have to multiply it by the cross-sectional area of each one of those loops, and in a somewhat simplified way am I thinking now of it as having n of these circular loops, which of course is not exactly accurate, but it's very good approximation for this staircase type surface that moves up. So now I must multiply it by n, so I get an n square here, and I now have the current I through, which pokes through n times. And here is my pi r squared. I already had the I, sorry. This is b. I must multiply b by n, that gives me a b squared, and I must multiply it by the area, which is pi r squared. There is no extra I here. This term is called the self-inductance. It's just a name. It's purely geometry. It is nothing else. So this is simply called L times I. And it is no surprise that L is proportional to n squared. One n comes in when you calculate the magnetic field. That's proportional with n. And the other n comes in when you recognize that the current pokes n times through that surface. Okay, and so this is the magnetic flux going through my open surface. And if you ever need the time derivative, well, then you would get L di dt. And of course you have here this minus sign. If your solenoid were a toroidal system with radius r0, then this L simply became 2 pi r0. Now that we have prepared this, and we keep in mind that the open surface integral B dot dA equals Li, we can now tackle the last problem that I will do today from the assignment. It's not the last problem that I will do today, but the last from the assignment. Plus, minus, a switch S1, switch S2, resistance R, this point is called A, this point is called B, self-inductance, which we now understand, we call a solenoid a self-inductance. The R was 400 ohms, and the L had an SI value of 0.2, which is in units of Henry. I close S1, the current will increase through this circuit, nothing through here. L will oppose the current, but ultimately L can no longer fight the current, and there is going to be a current flowing through here. And E, which is the EMF of the battery, through Ohm's law equals IR. And so I, you can easily calculate, equals 0.3 amperes. At that moment, I close S1 and I open S2, and let's assume I can do that at one and the same time. So my circuit now looks rather different. I now have a circuit that looks like so. R, L, 400, 0.2, and I have at one particular moment in time, and the current changes with time, the current will decrease in time, I of t. There is an electric field only in the resistor. There is no electric field in the self-inductance. The self-inductance is made of superconducting wire. No electric field in here. We call this point A, we call this point B, and we call this point C. And at time t equals 0, we have 0.3 amperes. L is opposing the decay of the current. Of course it will decay because there is heat dissipation in the resistor, but L has the ability to oppose that. It slows the decay down. I use Faraday's law, which says an induced EMF is the closed loop integral of E dot dl, and that equals minus d dt times the integral over the open surface B dot dA. This is an open surface, and through here is that peculiar staircase surface. Whenever I go around, I told you earlier, I always have disciplined myself to always go around in the direction of the surface, that I never get into trouble with positive plus and minus signs. I already know, by the way, that this current is decreasing, so clearly what the self-inductance will do, it will try to keep the current going in this direction, and so it will try to introduce an E-induced in this direction to keep the current going. It fights the decay of the current. So I'm going around this way. I start at point A, closed loop integral of E dot dl, and I'm going to cut it in 3 sections, in going from A to B through the resistor, E dot dl, plus in going from B through C through the self-inductor. I just put an L here, which is my shorthand notation, plus back from say 3 to C to A through the wire, and that now equals minus d dt B dot dA. And this value, we already know, equals L times I. I, not E, L times I. What is the integral A to B of E dot dl through the resistor? There's an E field in this direction, it is positive, and it is IR. At that moment in time, but I'll drop that T. What is the integral E dot dl through the self-inductor. It's obviously 0, because the self-inductor is made of superconducting wire. There is no electric field inside the self-inductor, so this is 0. Here again there is no electric field, and so that's also 0. And so what do I get? I get IR equals minus ddt times Li. And so I want to stress, by the way, that Kirchhoff's law is for the birds. The closed loop integral going around all the way back to point A is not 0. It is minus L di dt. No Kirchhoff's law. Don't let anyone mislead you or persuade you. So I get IR equals minus L di dt. I bring the L di dt inside. There's nothing wrong with that. Plus L di dt equals 0. And I get, as a solution, you shouldn't have too many difficulties find this, a decaying E field, and it decays in the following fashion with a decay time tau, which is L over R, which in our case equals 5 times 10 to the minus 4 seconds.